Newton developed the three laws of motion that contributed to the fundamental understanding of dynamics, the one that answers the question what makes an object move. In addition to his accomplishments, he was curious about the motion of the planets and the moon. He wondered about what keeps the moon in its circular orbit near the Earth. Newton was inspired to study gravity when he noticed an apple drop from a tree. In connection to what he was wondering about, he contemplated that if there is gravity at the tree, and even at the mountains, then perhaps it also act all the way to the moon. Newton proposed that it is the Earth's gravity that holds the moon on its orbit. But many thinkers had trouble accepting this concept. The moon and Earth are apart. Thus the force of gravity is acting at a distance, while the typical force acts through contact, like when you're pushing or pulling a door. But gravity acts without contact. Newton claimed that the Earth exerts gravitational force on a falling apple and on the moon, even though there is no contact, or even if the two objects are far apart. Newton successfully proved this concept, and even calculated the magnitude of the gravitational force that the Earth exerts to the moon. From his experiment, he concluded that the force of gravity is inversely proportional to the square of the object's distance from the center of the Earth. Thus, the gravitational force exerted by the Earth decreases with the square of the distance, denoted as r. He also realized that gravity also depends on the mass of an object. Additionally, according to Newton's third law of motion, when Earth exerts its gravitational force on any object, there is an equal and opposite reaction on the Earth. Furthermore, he concluded that it is the gravitational force that acts on the Sun and each planets to keep them in their orbits. The law of universal gravitation states that every particle in the universe attracts every other particle with the force equal to the product of their masses, and inversely proportional to the square of the distance between them. From this, Newton was able to derive the equation for the universal law of gravitation, where the force of gravity is equal to the masses of the object acting on each other, at a square of distance r. G is the universal constant equal to 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. This was determined by Henry Cavendish. He was the first to measure the force between two ordinary objects. He performed this experiment 100 years after Newton published his law. The equation for the gravitational force can be used to calculate the mass of the Earth. Henry Cavendish was the first to calculate the universal constant g, thus he was also the first to calculate Earth's mass. This equation can be applied to the gravitational force between the Earth, with mass me, and an object, with mass m that is near the Earth's surface. Remember that the weight of an object is equal to mass times the acceleration due to gravity. Equating the two equations give acceleration due to gravity is equal to universal constant times mass of the Earth over square of the distance. If the acceleration due to gravity, universal constant, and the distance r or the radius of the Earth are given, then we can calculate the mass of the Earth. Take note that the object is near the Earth's surface, therefore the distance is approximately equal to the Earth's radius. Now, the mass of the Earth is equal to the gravitational acceleration, times the square of the Earth's radius, over the universal constant. The calculated value is 5.98 times 10 to the 24 kilograms. Using the Earth's mass, we can now calculate the value of acceleration due to gravity at different locations of the Earth. For example, we are going to estimate the value of acceleration due to gravity on the top of Mount Everest, that is 8,850 meters above sea level. To calculate, we need to add the Earth's radius and Mount Everest's height above sea level. This is equal to 6,389 kilometers or 6.389 times 10 to the 6 meters. We can use equation we derived before to find the acceleration due to gravity. It is now equal to the universal constant times the Earth's mass over the sum of the Earth's radius and Mount Everest's height above sea level. The acceleration due to gravity is 9.77 meter per second squared. From this calculation, we found out that the acceleration due to gravity at the top of Mount Everest is not 9.8 meter per second squared but equal to 9.77 meter per second square. This is because Earth is not a perfect sphere, it also has mountains, valleys and bulges, moreover, its mass is not distributed uniformly. The Earth's rotation also affects the value of acceleration due to gravity. However, in physics, we still use 9.8 meter per second square for practical purposes. I hope you learned something in physics today. If you enjoyed this video, please let me know by clicking follow. Thank you for watching.